All right, ladies and gentlemen, welcome back to another video with Mr. Kenton and HL Chemistry. And we're going to be continuing our discussion on light and how that pertains to electron configuration. We're going to be looking at how our understanding of the hydrogen emission spectrum gave us some insight as to the quantized nature of electrons and how when electrons are excited, they move, and when they move, they give off specific wavelengths and frequencies of light. And then we're going to be transitioning into the nuts and bolts of the quantum mechanical model by looking at the different types of orbitals that exist where we can find probable locations for electrons. So I'm excited about sharing this information with you today. So I hope you're ready. Hope you put your thinking cap on. Let's get to this. So as we look at this video, what we should be able to do is understand that the line emission spectrum of hydrogen provides us with evidence for the existence of electrons in discrete or specific energy levels, which converge as we get to higher and higher energies. Okay. Now, skills, application pieces from that piece of knowledge is that we should be able to describe the emission spectrum of the hydrogen atom, including the relationship between the lines and energy transitions as it pertains to the first, second, and third energy levels of an atom, okay? And so if that doesn't make sense, it'll get clearer here as we go forward. So when we think about hydrogen as the line spectra for hydrogen specifically, what we know is that the hydrogen atom gives out energy when an electron falls from a higher to a lower energy level. It releases energy, right? So it's going from a higher state to a lower state that releases energy, right? Likewise, if we're going from lower to higher, it would be taking in energy. It would be taking in an energy that is corresponding to that particular transition. So that should not be anything that's new to us. Now, we're going to make a connection here, and this is going to be applicable across the board. At least it should be. Right? That hydrogen is going to produce visible light when an electron falls to the second energy level. So, for example, if an electron is in the fifth energy level, for example, and then it moves into the second energy level, then for hydrogen, it's going to produce a visible light emission. And that's going to be always the case. When an electron moves from a higher energy level to n equals 2, it's going to produce visible light. Now, if the transition is it's in a higher energy level and it moves to n equals 1, so that energy level that's closest to the nucleus, this is going to be a higher energy change because closer to the nucleus is lower in energy. And so what that's going to do is it's going to give off a UV form of light. So therefore it has higher energy. That should make sense. Now, when an electron falls to the third or higher energy level, so let's say we go from n equals 6 to n equals 3, within the hydrogen atom, what we see is that it's going to produce an infrared radiation, right? So now notice when it goes from anything higher to n equals 1, it's UV. When it's from anything higher to n equals 3, it's IR. We only get that visible emission when we move from something higher to n equals 2. Okay, and again, this is unique specifically to the hydrogen atom. Now, as we look at that, continue to look at hydrogen as an example here, what we see when the energy levels are drawn around the nucleus, they are spaced farther apart near the nucleus and much closer together at higher energy levels. And so if you think about the Bohr model of the atom, what you'll see is typically like n equals 1 takes up a specific amount of space, but then n equals 2 is pretty far apart. And think about the ladder that we referenced in the previous video of how the steps are uneven. Well, that's what we're trying to model here and trying to communicate here. That once they get farther and farther from the nucleus, those energy levels start to get closer and closer to each other in terms of moving farther away from the nucleus. Now, if you had to draw the line spectrum for hydrogen, you would draw the lines closer together at higher energy, right? And so the lines that are on the line spectrum represent energy emitted when an electron falls from higher energy to lower energy levels. And so let's just take a look at what is the line spectrum of hydrogen. What does it look like? So on the top, you have the absorption spectrum for hydrogen. And so what that's showing you is that when electrons within hydrogen's atom absorb light with those specific frequencies, it absorbs that and the electron moves. Now, likewise, when the electron is moving from a higher energy level to a lower energy level, these are the specific colors of light that are given off. And so you've got 1, 2, 3, 4, 5, at least as I'm looking at this, looks like there are 5 different emissions that can take place within the hydrogen atom that are at least visible light. And so notice that it says that the hydrogen alpha line at 656 nanometers, that's the transition from N equals 3 to N equals 2. I believe what that's getting at is the most common emission as it pertains to the hydrogen atom. And just remember, this isn't showing all of them. This is showing all of the transitions that are in the visible spectrum, right? So even though this is going from N equals 3 to N equals 2, we've got some that could be this purple, we've got that blue, we've got that bluish green, and then we've got the red. So depending on, I guess you could say, depending on what part of the second energy level it's moving into, maybe it's moving from the 3s to the 2s, or maybe it's going from the 3s to the 2p. And so we get these different transition lines that we need to consider. All right. So now that we've looked at line spectra, we're now going to start to frame this within the quantum mechanical model and start talking about energy levels and subshells and SPD and F orbitals. So our understanding key idea here is going to be that the main energy level or shell is given an integer number n and can hold a maximum number of electrons, which is 2n squared, right? And remember, n is essentially equal to the row on the periodic table, right? When n equals 1, that means you have 2 times 1 squared, so 2 electrons that are in the first energy level. That makes sense because there's only 2 elements on the first row. Likewise, if it's the second energy level, second row, you got 2. On the second energy level, you got 2 times 2 squared, so 2 times 4 is 8. Well, would you look at that? We've got 8 elements on the second row, right? So on and so forth. Now, other understandings, key ideas that we need to kind of take away from this. A more detailed model of the atom describes the divisions of the energy levels into our SPD and F sublevels of successively higher energies. And so that should make sense. That's how we get to our electron configurations. And so we'll talk about those more in depth here shortly. All right, so let's first talk about energies of orbitals. So within an energy level, right, we could have SP, D, or F orbitals, and it's important to recognize that the S orbital is always the lowest in energy. Then you're going to have the P orbital, then the D orbital, and then the F orbital within that energy level is always going to be the highest in energy, right? So when you start talking about within the, for example, the 4th energy level, the 4s orbital is the lowest in energy, then it would be the 4p orbital, and then should your element have a 4d subshell, then that would be the next highest in the 4th energy level. And if it's far enough down and it goes to 4f, the 4f orbital would be the highest energy orbital within the 4th energy level. Hopefully that makes sense. Now, orbital energies. I like this diagram over here. If you remember, there's the off-ball principle, which states that we need to fill in an electron configuration by placing the electrons in the lowest energy orbital first, and then move into higher energy orbitals. So the off-ball diagram shows us the energies of the various orbitals, and then our lowest energy orbital is the 1s orbital, and as you follow those arrows, energy increases. So you would go to 1s, then you'd go to 2s. Once you fill in 2s, you go to 2p, and then to 3s. Once you go to 3s, you'd go back to 3p, then move into 4s. Then after 4s, you'd move 3d, 4p, 5s. Once you filled in 5s, you'd go 4d, 5p, 6s. Then once you filled up 6s, you'd move 4f, 5d, 6p, 7s. And then likewise, it'd go 5f, 6d, 7p. And should we get to that point, because we're not there yet, you would move into n equals 8, which would start with 8s. Now, the thing that I like about this diagram over here is it's telling you part of the quantum number information. So when L equals 0, that corresponds to an s orbital. When L equals 1, that corresponds to a p orbital. When L equals 2, that corresponds to a d orbital. And when L equals 3, that corresponds to an f orbital, right? So just interesting information, good things to kind of remind ourselves of and refresh ourselves with. Now, as we're moving forward, you should be able to recognize the shape of s atomic orbitals and the px, py, and pz atomic orbitals. So essentially I'm asking you, what are their shapes? What do they look like? And so let's first start with our s orbital. So remember, the smallest orbital is the s orbital. This is also our lowest in energy within a given energy level. And so the quote s orbital has only one shape. And if you remember, it looks like a sphere, and it holds 2 electrons, right? So any s orbital, regardless of whether it's a 1s or a 6s orbital, it can only hold 2 electrons. It's spherical in shape, and it's the lowest energy orbital. And so when we think about this, this would represent the probability of where one of those 2 electrons could be found within that particular orbit within that energy level. Okay, and so all s orbitals have that general shape. The only difference between like the 1s and the 2s is that the 2s is just larger because it's in the second energy level. Likewise, as you move further, like 6s would be even larger than the 2s, right? But it would still hold only 2 electrons. Then we've got p orbitals, right? So remember, these are the ones that kind of look like a dumbbell. So the second orbital shape is the p orbital shape. And there are a total of 3 different p shapes, each holding 2 electrons. And so because there are 3 p shapes that each hold 2 electrons, that's a total of 6 electrons in total that could be found in the p orbital, right? And I'm liking the diagrams here. And so what they're showing you, the px orbital is the p orbital that's oriented along the x-axis of the plane. The py orbital is oriented along the y-axis. And then our pz orbital is oriented along the z-axis in 3-dimensional space. And so the p orbitals, they're dumbbell shaped, and they're arranged at right angles with the nucleus at the center. So notice that in all of those representations, in a sense, the origin at 0, 0, 0, that's where the center of the atom, the nucleus, is going to be located. Okay, and so knowing those particular shapes, the shape for an s and a p orbital, that's important. And being able to kind of represent them, to be able to draw them, that's even useful when you start to look into bonding, when you start talking about orbital overlap and how you get into sigma and pi bonding, things like that. That's why it's important to recognize these particular shapes. Now, please remember, p orbitals are higher in energy than an s orbital. So, for example, within the second energy level, you have 2s orbital, and then you have the 2p orbitals. The 2p orbitals are higher in energy than the s orbital, but each p orbital, the px, py, and pz, are equal in energy in relation to each other. All right, next up, we've got our third orbital shape, which are our d orbitals, which are a lot more complicated. Right, the third orbital shape is the d orbital shape. Remember, the d orbitals become apparent once you move into the transition metals on the periodic table. So starting on the 4th row, that's when you first encounter your first set of d orbitals. Now, there are a total of 5 d orbital shapes, and notice they have weird designations. So you've got the dx squared minus y squared, you've got the dxy, you've got the dyz, you've got the d, I'm assuming that's going to be xz, and then you've got the dz squared, right? So those are your different designations of d orbitals. Now, because you've got 5 orbital shapes, that means you get a total of 10 electrons in the d orbital. And if you think about it, if you count the number of elements that are in the row on the transition elements, it corresponds to 10. Now, in terms of orbital energies, in a given energy level, for example, like the 3rd energy level, for example, there's the 3s, the 3p, and the 3d orbital. Well, in terms of arranging those orbitals within the 3rd energy level by energy, the 3s orbital would be lower in energy. Then you'd have the 3p orbitals that would have higher energy than the s orbitals, but each p orbital would be the same in energy. And then the d orbitals would be above the p orbitals, so higher in energy, but each of the 5 would be the same energy. And that's, if you remember, the term that we use to talk about the energies of the 5 d orbitals being the same, we say that they're degenerate, that they have the same energy. All right, and then our last orbital shape are the f orbitals. All right, I'm not even going to pretend to try to tell you what those correspond to, but you see those diagrams in the bottom right corner there. The last orbital shape is the f orbital shape, and those are going to correspond to the elements that are in your lanthanide and actinide series, or the rare earth metals, right? So the f orbitals have irregular shapes due to quantum tunneling. Please don't ask me what quantum tunneling is. I have no idea. That's one of the first times I've seen this word. I'd have to do some research and understanding what that means. But they have these funky shapes because of this phenomenon known as quantum tunneling. Now, for your f orbital, there are 7 f shapes. And so within those 7 f shapes, you have a total of 14 electrons in the f orbital. Now, again, if you count the number of elements that are in the f block, so in the lanthanides and actinides in one row, there are 14 elements, therefore 14 electrons, right? So we start to see how the quantum mechanical model really matches up nicely with our periodic table. Now, electrons that are in the f orbitals are very high in energy, okay? And it has to do with the fact, I would imagine, the irregular shapes due to that quantum tunneling. All right, and I believe, ladies and gentlemen, that is the last slide that we need to take a look at as it pertains to the different orbitals within the atom where the electrons can reside. So I hope this was a good, insightful video. I hope it's a good reminder of things that you've previously learned. If you do have any questions, please don't hesitate to ask. Ask me in class, ask me in office hours, but please just let me know if you got questions. I appreciate you guys watching this video. Hope it was insightful, and I look forward to seeing you guys again soon.